Hi, welcome to R&AC Academy. My name is Ram Prasad. Let me give a small brief about me. I did my masters in R&AC and then I worked for 25 years with the various organizations involving in product development and technology innovation functions. I had 5 patents filed on my name. Out of my passion, I transitioned into teaching. Presently, I am into coaching GATE and IES aspirants on R&AC subject. I also conduct workshop on R&AC systems, faculty development programs, etc. for the engineering colleges. Recently, I conducted webinars for the members of ISHRE and ASHRE. Coming to this program, I am presenting here with a series of lectures on refrigeration systems for the benefit of the students and professionals. I believe these lectures will be of great help and learning to all of you. This is the 7th lecture in the series of lectures on refrigeration systems. In this lecture, we will discuss the various factors that influence the performance of VCR cycle. Let us start with the first one, that is pressure ratio. It is the ratio of condensing pressure to evaporating pressure, PC divided by PE. It is obvious to say that if the PC is increased or the PE is decreased, the PR, pressure ratio, will increase and vice versa. Let us now see how the pressure ratio will be influencing the performance of VCR cycle. As the pressure ratio increases, work of compression increases, RE decreases, COP decreases. And to sum it up, whenever the pressure ratio is increased, the consequences on VCR cycle performance are negative. Let us take up the second factor that influences the performance of VCR cycle. That is evaporating pressure or evaporating temperature. To understand this phenomena, let us pull back the pH diagram with a baseline VCR cycle 1, 2, 3, 4 plotted on it. Let this baseline cycle be operating between PC and PE or TC and TE. Both are same. And also let RE and W be the refrigeration effect produced and work input given to this baseline cycle. Let us now increase the evaporating pressure from PE to PE dash. That automatically increases the evaporating temperature from TE to TE dash. As the evaporating pressure is increased, the pressure ratio decreases. Let us now plot the VCR cycle for these new operating conditions. 1 dash, 2 dash, 3 and 4 dash is the new cycle which is operating between PC and PE dash. And for this cycle, the refrigeration effect produced RE dash clearly appears to be greater than the baseline value, and the work input needed to be given to this new cycle, that is W dash, is clearly less than the baseline value. Let us now decrease the evaporating pressure from PE to PE double dash. This automatically reduces the evaporating temperature from TE to TE double dash. As evaporating pressure is reduced, the pressure ratio increases. Let us now plot the VCR cycle for these operating conditions. 1 double dash, 2 double dash, 3, 4 double dash is the new cycle that operates between PC and PE double dash. And if we look at the refrigeration effect produced by this new cycle RE double dash, it is clearly less than the baseline value, and the work input that is needed to be given to this new cycle, that is W double dash, is clearly greater than the baseline value. Therefore, with increase in evaporating temperature, the pressure ratio decreases, refrigeration effect increases, work input decreases, COP increases. Hence, whenever the evaporating temperature is increased, the consequences are positive, or whenever the evaporator temperature is decreased, the consequences will be negative. Let us take up the third factor, that is condensing pressure or condensing temperature. Again, to understand this phenomena, we will pull the pH diagram back with the baseline VCR cycle 1, 2, 3, 4 plotted on it. Let PCPE and TCTE be the operating conditions for this baseline cycle, and let RE and W be the refrigeration effect produced and the work input given to this baseline cycle. Let us now decrease the condensing pressure from PC to PC dash. That would automatically reduce the condensing temperature from TC to TC dash. As the condensing pressure is reduced, the pressure ratio also will be reduced. Let us now plot the VCR cycle corresponding to these new operating conditions. 1, 2 dash, 3 dash and 4 dash is the new cycle that operates between PC dash and PE. The refrigeration effect produced by the new cycle RE dash is clearly greater than the baseline value, and the work input that is needed to be given to this new cycle, that is W dash, is clearly less than the baseline value. Let us now increase the condensing pressure from PC to PC double dash. With this, the condensing temperature automatically increases from TC to TC double dash, and as the condensing pressure is increased, the pressure ratio increases. Let us now plot the VCR cycle corresponding to these operating conditions. 1, 2 double dash, 3 double dash and 4 double dash is the new VCR cycle which operates between PC double dash and PE. The refrigeration effect produced by this new cycle RE double dash is clearly less than the baseline value, and the work input that is needed to be supplied to this new cycle, new VCR cycle, W double dash, is greater than the baseline value. Therefore, with the decrease in condensing temperature, pressure ratio decreases, refrigeration effect increases, work input decreases, and finally COP increases. Hence, whenever the condensing temperature is decreased, the consequences are positive. Or whenever the condensing temperature is increased, the consequences will be negative. The next factor is subcooling. What is subcooling? When the liquid is cooled below its saturation temperature, then the liquid is said to be subcooled. To understand the phenomena of subcooling, first we should know where does the refrigerant exist in saturated liquid state. To understand this phenomena, let us pull this pH diagram with the baseline VCR cycle 1, 2, 3, 4 plotted on that. Let PCPE be the operating pressures and TCTE be the operating temperatures. Also, let us say RE and W be the refrigeration effect produced and work input given to the baseline cycle. Among these 4 states, 1, 2, 3 and 4, we could clearly see that the refrigerant exists as saturated liquid at state point 3. And whenever the saturated liquid refrigerant at state point 3 is cooled below TC to, let us say, state 3 dash, then the liquid is said to be subcooled. So, at 3 dash, the refrigerant is subcooled to temperature Ts, but the pressure remains unchanged at PC. Please remember, during subcooling, the pressure of the refrigerant does not change. So, at state 3 dash, temperature Ts and pressure PC, the refrigerant will now enter into the expansion device, gets expanded from PC to PE to state 4-. The corresponding enthalpy value is H3- or H4-. Now, at 4-, the refrigerant will be entering into the evaporator to produce a refrigeration effect of RE-. The RE- is clearly greater than the baseline RE. On the other side, the work input to the cycle does not change. Therefore, with subcooling, pressure ratio does not change, RE increases, W remains unchanged, and COP increases. The next factor is superheating. Let us understand what is superheating. When the vapor is heated above its saturation temperature, then the vapor is said to be superheated. To understand this phenomena of superheating, first we should know where does the refrigerant exist in saturated vapor state. For that, let us again pull the pH diagram with the baseline VCR cycle 1, 2, 3, 4 plotted on it. And let this baseline cycle be operating between PC and PE or TC and T. Also, let RE and W be the refrigeration effect produced by the baseline cycle, and W is the work input given to the baseline cycle. So, among these 4 states, 1, 2, 3 and 4, we could clearly see that the refrigerant exists in saturated vapor state at state point 1. And the temperature of the refrigerant at state point 1 would be TE. And whenever the saturated vapor refrigerant at state point 1 is heated above T to, let us say, state point 1-, then the refrigerant is said to be superheated. The enthalpy corresponding to state 1- be H1-. Now, the refrigerant at state point 1- will be entering into the compressor where it gets isentropically compressed to attain the state 2-. And at 2-, the refrigerant will be entering into the condenser. So, 1-, 2-, 3, 4 is the new superheated VCR cycle we got. If the enthalpy corresponding to 2- is H2-, then W- would be the work input to be given to the new superheated cycle 1-, 2-, 3 and 4. The important question here is that how W and W- are related. If the process line 1, 2 and 1-, 2- are parallel, then W and W- would be equal. However, these two are not parallel. How can we say that? There is one typical characteristic to the isentropic lines. That is, the isentropic lines become flatter as they go away from the saturated vapor line. Therefore, 1-, 2- and 1, 2 lines would not be parallel. Then, as 1-, 2- process line is away from the saturated vapor line, it would be flatter when compared to process 1, 2. Hence, the value of W- would be greater than the baseline value W. To sum it up, with the superheating, PR does not change, pressure ratio does not change, work input needed to be given increases, and refrigeration effect increases if superheating happened inside the evaporator, else no change. Then how about COP? Because of some uncertainties in this case, we cannot make a generic conclusion on COP. With this lecture is completed. In case you have questions, doubts, queries, etc., please feel free to write to me. The next topic in this series is on volumetric efficiency of compressors. See you then. Thank you very much.